the distance and the current.
All right, so chances are I should have given you this value, or you should know by now that the permittivity of free space is 4 pi times 10 to the minus 7. So with that question, basically, you're using this formula that says the flux density is equal to mu naught times I divided by 2 pi r, where r is basically the distance, right, away from the wire, right? So I thought that you would have been able to can pick up that mu naught would have been that value, right? So all you'd have done there is to just go ahead and put in mu naught, which is the permittivity of free space, times the current, divide that by 2 pi times the distance away from the wire, and you would have found out that information. What was the next question related to?
I don't see any other
questions in the group chat.
Repeat that for me.
I said I found it and I sent it in the group chat.
Okay. Let me see.
You see it, sir?
Yeah, man, I'm looking at it. I don't know why you don't have it though. So the next part of the question was that to calculate the flux density at the center of a 200 turns coil, circular coil, and it says it has a radius of 0.25, carrying a current of 0.5 amps. As it relates to that, this is the equation that you would have used to find that, because this is talking about a circular coil. So you have one equation for a straight wire that you can use to find the magnetic flux density. So you have to remember these formulas. You have to remember them. You have to come up with your way of remembering them. I don't know how you can remember them. You have to just pick your way of remembering these formulas. And there's another way we can derive. I don't know how they derived it, so we can't just say, all right, let's derive it or whatsoever. So you'd basically be using this to say pi, not pi, but B, which is the magnetic flux density, is equal to mu naught times N, where N is the number of turns, times the current, divided by 2R, where R is going to be the radius. All right?
Okay, sir. I'm going to attempt it.
Then the next part is inside a long solenoid. So they want us to calculate the flux density, inside a long solenoid. Now, as it pertains to a solenoid, there is a specific equation as well to find the magnetic flux density. This one is now B is equal to mu naught times small n times I. All right. So you would essentially use that information. As it pertains to small n is equal to, is basically what we call the turn density, which is the number of turns per unit length. So if the question had said that, it says calculate the flux density inside a solenoid with 220 turns per centimeter, that means that your small n is that value, because as we said that small n is equal to the turn density, which is just saying the number of turns per unit length. So for every centimeter there is 200 turns. That's just what it's saying, and it's carrying a current of 200 milliamps. So you have all information there. So you just need to just prioritize and know these equations, right, and know which one to use at the given time. Don't neglect this information as well. The part that says n is equal to big N divided by L.
Okay.
Yeah, so you still have those to complete then. All right?
All right, sir.
All right. All right, we're moving forward now. Um, yes, so this is where we are essentially going to begin. Just to do a little quick recap about Fleming's left-hand rule. As you can imagine, that whenever a current wire is before we even talk about this entire thing, you have to remember that once current is flowing through a wire, there will be a magnetic field that is generated around the wire. So that is point blank. We ought to know that. Now, whenever we have a current wire that is placed within an external magnetic field, we would have agreed to say that the wire will experience a force. Now, there's a particular method through which we can determine the force on the wire, right? And that is by using what we call the Fleming's left-hand rule. Now, just like how you see the image being displayed right here, that's the same way your hand has to be positioned. So clearly your thumb is used to represent the force or the motion. So wherever your thumb is pointing, that is just telling us that that is where the wire is going to move towards. Now your first finger, right, your pointing finger, is used to predict the magnetic field of the external magnet. So in a sense, B right here, this finger is showing you the external magnetic field. So let's recall that the wire is being placed inside of a magnetic field. What is that magnetic field? It's what is coming from the bar magnet. Now, always remember that whenever you have a thing like this, like I have a north and I have a south pole looking like this, what you would see is that there are going to be straight lines coming from the north going into the south. At all times when it's like this, your magnetic fields move out of the north, goes into the south at all times. So as you can see here, this is your north, and the magnetic fields are going into the south. All right, so this right here is what we call the external magnetic field. We're not concerned about the magnetic field around the wire, even though that plays a factor in the whole thing here, but we are not concerned about that for now. The next thing that we would be concerned about is the direction of the current. The question told us that, well, not the question, this diagram told us that the current is going inward. So in a sense, we can say that the current is going into the paper. Let me just draw my magnetic field going across like this. So what you would essentially do is take your left hand, position your fingers and your thumb as such, as you're seeing on the diagram. And what you would do, you would highlight the magnetic field first. So your pointing finger must be pointing going across the screen like this. Then after that, you have to maintain that position, meaning that if you know that your magnetic field is going from west to east, right, then that finger has to remain in that position, meaning that it has to be pointed in that direction at all times. So the next best thing I could do in order to get or to prove that the wire is going to go down is to highlight where the current is flowing. The current is flowing into the paper. So what you would do is to just rotate your arm without changing the direction of the magnetic field, and then you would see that your thumb is pointing down. So what this tells us is that the wire is experiencing a force down, a downward force. I don't know if I got if my quality went down in terms of the internet.
No, sir, I'm already.
Okay, good. Right. Campbell, were you able to do that to see whether it makes sense to you in terms of the Fleming's left-hand rule?
Yes, sir. I was this already. So yeah, I understand.
All right, wonderful. All right, now we're going to move a little bit away from the wire, and now we're going to look at a charged particle as how it moves inside of a uniform magnetic field. Now, you're going to see several things occurring here, but one of the first things that we want to highlight, right? It says that for charged particles, usually electrons traveling within a wire at right angle to the uniform magnetic field, it is possible to find the force acting on each charge. It says, firstly, we have to take the force that is experienced on the wire. So the first thing that you would start out with is to consider the force that is being experienced on the wire, and that force is equal to Bill, basically the magnetic flux density times the current times the length of the wire. What we are doing here, guys, is that you have a piece of conductor. You have a wire, right, that is placed within a magnetic field. Inside of the wire, remember now, current is flowing through the wire. So the charges that are inside of the metal, which are actually electrons, those charges are going to essentially experience a force. What we're trying to do is to see what the force really is in this case. So to begin, we have to start out with the overall force that is experienced on the wire, which is the B field, the external B field, times the current in the wire, times the length of the wire that is inside of the magnetic field. Having said all of that, right, we can then recall from definition that current is the rate of flow of charge, right? That current is the rate of flow of charge, and we write it as this to say that current is equal to Q divided by T, where Q is the charge and T is the time. That is what current is. Now, as you can imagine, if electrons are traveling from one end of the conductor to another end of the conductor, then we can now agree that those electrons are going to have what we call a velocity, because they are moving, so they will have a velocity. Now, let's just look at something here. Let me just see if I can draw this a little bit better, right? So this is my conductor that is within a magnetic field. Let's just imagine that the magnetic field is around here. This is probably the north or the south, and then you have another magnet below here, which is going to be the north. Yeah, I believe this is fine as is. Yeah. So having said that, right, these particles, as you can see right here, the wire, right, has a particular length that is inside of the magnetic field. Now, when those electrons are in that magnetic field, we're saying that they are going to experience some amount of velocity because they're moving from this end all the way to this end. So to find the average speed or the mean speed that these electrons would have, firstly, you would need to find the distance that they're traveling. That distance would be the length of the conductor that is inside the magnetic field. And you would obviously need to know the time that they're taking to travel from one end to the other, to the other end of the conductor. So with that being said, we're essentially finding the speed right here. So what we're looking at here is to say that speed is equal to the length of the conductor in the magnetic field divided by time. Now, we can do a little bit of substitution. Or what we could do is we're going to make T become the subject. Go ahead. Yes,
I was asking to repeat that, please.
What we're going to do here with this equation, we are going to make T. Let me see if I want to make T become the subject. Give me a second here. So if I substitute that, yes, let's try something here. Let's try and make T become the subject, and let's see what's going to happen. So if I make T become the subject in this equation, I would have if T becomes the subject, that is what? L upon V. Okay, yeah. Yeah, so let's make T become the subject. When T becomes the subject, T is now equal to L upon V. What we're going to do now is to basically put in some information in our formula. So force is now equal to B times I. Well, you no longer have I in the equation. We're going to replace I with Q upon T, right, times L. But just now we said that T is equal to L divided by V. So in essence, my force, if I substitute T in that equation, I now have force is equal to B times Q times L, right? And since T is dividing here, we're substituting for T with L upon V. I could say divide by L upon V, because that's the same thing. Because T is dividing and we know what T is, we can just write it as such. Whenever we're dividing fractions, we normally find the reciprocal. So here we are now. We have force is equal to B times Q times L. So we're going to multiply and find the reciprocal. So that is going to be V upon L. Now here we're seeing that L and L is going to cancel out. So what we're left with is this equation to say that force is equal to B times Q times V. So this is the force that the charged particles inside of the conductor will essentially experience, right? So that is the force. So you have two equations that are related to force on a current wire. You have this one. You have this one here. This is just talking about the entire wire. Now, whenever we're talking about the charges that are within the conductor, then this is the equation we use to find the force on those charged particles. Let me know if you guys see what I did here as relates to the proof, and we must know to prove this, right? We must know to prove it. Hope you guys are taking notes, because we don't have time to give away. But let me know if you have any questions, though.
No, sir.
All right, Isabel, is she still here?
Yes, I'm still here.
All right, just wanted to check. All right, now having said all of that, right, now we're going to look at a diagram to just see what is really taking place here. Right, I think this was the proof on a whole that is being displayed here, right? Just showing you everything that I just wrote a while ago. But you see now, this is a little bit different now, because what you're actually seeing now, you see these X that you're seeing here, right here, these X's mean that the magnetic field is going into the plane of the paper, right? I'm going to show you soon why we need to talk about that. But just be very, very, very careful that whenever there are several ways because if you can remember, we use X for something else. Anybody remembers what we use X for in the whole magnetism, well, the whole magnetism lessons that we have been looking at? The symbols that we use, they're critical because somebody, go ahead.
Isn't like the X supposed to be, well, what I remember you telling me, sir, was, you know how a dart has, I think it's the X in the back, so that means like that the electrons are going, or the charge is going into the specific direction.
The who? The what? The current? That's what you said?
Well, what I remember you once saying, sir, is like you used an example of like a dart, and I think you said like when charge is going like inside, it will be a dot, and then when it's coming out, I think it'll be an X.
You have the concept, but it's the other way around, right? Whenever we see an X, right? Let's just imagine that this is a wire, and around the wire, right, there is some magnetic field lines. Now remember now that for this, if we wanted to map out the magnetic field around this wire, right, we would have to use the right-hand grip rule, where whenever you see an X in the center, the X means that the current is going into the paper. Into the paper. So this one right here, the X means current into the paper. Now when you have the dot, by the way, tell me what direction the magnetic field would be going around this wire, the one with the X. You heard the question?
Wouldn't it be going clockwise?
Yes, it will be going clockwise. It will be going clockwise.
And then with the dot, it will be going anti-clockwise.
Precisely, because the dot means that the current is going out of the paper, right? So anti-clockwise means that the magnetic fields around the current wire will be going like that, right? So that is something that is key practice and key knowledge that we have to remember. But the thing about magnetism is that sometimes they repeat themselves in terms of using the things, because what we're going to do here, right, is that whenever we want to represent a magnetic field going into the paper, we are also going to use X to represent that. So you now have to split your brain and put one information across to say, all right, we can use it for current, and now we can use it for magnetic field. So the X here means that the current, the magnetic field rather, is going into the paper. What if you were to see some dots? The dots would essentially mean that the magnetic field is going out of the paper. So these are stuff that we have to remember, because if we don't, then when you see it, you might think you're talking about the current, but they're not really talking about the current. They're talking about the magnetic field. So just be mindful of that. If I were to tell you to draw, magnetic fields going into the paper, then you would be drawing X's. But if I tell you now to draw a magnetic field going out of the paper, then you would
So
Go ahead.
one question, right? So if it were dots in the diagram, right, and it would be coming out of the paper, the arrows, would they be like the other way around?
Ask the question again.
Like if the current was going out of the paper with dots, right, Would the arrows, like in the diagram you just showed, would the arrows be like going the other way around? Like,
Are you making reference to this diagram over here?
no, I'm making reference to the diagram with the ball.
With the, I'm not sure which
With
part.
the um,
Which part of the screen you're talking about?
I'm talking about, like, you see the charge it has, like the blue charge,
Uh-huh.
and then it has, oh, that's the force and velocity.
Precisely. Yeah, in this regard, whenever we're dealing with the charge,
Oops.
no current is really involved in this regard, right? We're not talking about current, all right? So here we don't know. All right. So with this information here, the same Fleming's left-hand rule can be used to predict the direction of the charge in terms of where it's going to move in terms of the force, right? So what you would do is to take your right hand. You see what I'm saying? Take your right, not right hand, my bad. Take your Fleming's left hand rule with your fingers positioned in the correct way and everything. Then what you're going to do here is to ensure that your first finger is pointing into the screen. Then once your first finger is pointing into the screen, then your second finger, which represents your velocity now, that will be pointing from left to right. Then automatically you're going to see that the force on the charge will be going up in the air.
Okay.
I believe we got that.
Yes, sir.
So that is what is happening there. But as I said, just remember now that if you're seeing the x's, then the x's mean that the magnetic field is going inwards or into the paper. But if you're seeing dots, it means that the magnetic field, right, is going out of the paper. Remember now we're saying that we can use the Fleming's left hand rule to find or to predict the force on the charge, right? So just remember now that this B field is your first finger and the velocity is the second finger. Force is going to be the thumb. All right? Are we clear? I think so. Now,
Yes, sir.
I must point this out to you as it pertains to the movement of the electrons. The movement of the electrons is in a spiral way, right? So imagine that we're singling out an electron inside of the conductor. What we're going to essentially see is that the electron, when it is moving from one end of the conductor to the next end, it is not moving in a straight line. It is moving in a helical path. What just means that it is moving, going around in a circle and all of that. But this is where a little bit of knowledge of circular motion is going to come into play. We're going to look at that soon. But I just want you to see that, or to just remember that how the electron is, how the particle or the charge is moving. It's not moving in a straight line. It's moving in a helical path. Like it's climbing its way all the way up until it reaches the next end of the conductor. Comprehend? So it's almost like this. Imagine that the charge, imagine that we have the magnetic field like this. And the charge is here. Firstly, we know that if the velocity is like this, right? What we're going to see is that a force will be exerted upwards. Let me see if I can use a different color. So a force will be exerted upwards, but what you would realize, because we said now that the particle is moving in a circular path, at some point it's going to turn around like this, right? So that charge would essentially be rotating itself, you know, inside of the magnetic field as it moves around. Because we're saying that is how it moves. So it gets that force, right? And while getting that force, it is now moving in a a helical path all the way around until it reaches where it wants to go, right? Continuing doing what it's doing, right? So I think we're going to look at this in a different at a different angle very soon. Just give me a few seconds to just restart the meeting. I have less than a minute. Yeah. So what we're going to look at here, I have to repeat that, guys. So what we're looking at here is what essentially is taking place when we have various charge, right? And we know a charge can be positive or negative. So we just want to look at what essentially is going to take place. So let me just clear something here. So imagine that let's imagine that this is a positive charge for now, right? And if we go ahead and apply the Fleming's left-hand rule, our magnetic field is going into the paper, right? And our velocity is going in that direction. So at the end of the day, we would have seen that the force is acting up. That's for the positive charge. Now, remember that a positive charge is different from a negative charge. So if this was a negative charge, it means that it's going to behave opposite to what the positive charge is doing. So it means now that everything that we're doing here is going to be opposite, except for the magnetic field. The magnetic field is going to remain as is, but in essence, what we are seeing is that the velocity is going in this direction, right? So it's no longer going towards the right, but it is now going towards the left because of the fact that we're using an electron. So an electron is opposite of a positive charge. So because the charge is negative, right, it is going to behave opposite to that of the positive charge. The Fleming's left-hand rule would have clearly indicated for a positive charge that the force would be going up in the air. But now, what we're going to see is that because we're using an electron, the velocity is going to go towards the left. And so if you were to put your hand using the Fleming's left-hand rule according to that, so we're no longer using this velocity here, right? But we're now saying that the velocity is going in the opposite direction. So anytime you see this, guys, you have to remember, because what the questions will do sometimes, they will say that the electron is going in this direction, like it's going that way. But you now have to remember, say, all right, really and truly, if it's an electron, then it is going the opposite way in terms of the velocity, because electrons are opposite to protons. So that is the key thing there. So if we were to go ahead and find our magnetic field, which is going into the paper, find where the velocity is going using your second finger, then automatically you will see that your thumb is pointing downwards. Automatically you see that your thumb is pointing downwards. Confirm to me and let me know if that is something that you have seen.
Yes, sir.
Okay, wonderful. So what we're going to see happening now, in a sense, we can almost pretty much redraw the diagram on a whole, but we're not going to do that. We just know that the velocity is going that way now. So you would expect that the force would be going like this. And as the electron is moving in its path, we're now seeing that there is a constant force that is directing towards the center at different positions, right? So what this is giving us now, or bringing to our memory, is the whole concept of centripetal force. So what we can conclude is that the force acting on the charge, on the negative charge, is essentially going to be, going to be equal to the centripetal force. If we recall, centripetal force is equal to the mass times v squared upon r. So we always have to remember that, where v squared upon r is what we call the centripetal acceleration. So AC is equal to v squared upon r. So guys, as you can see now, everything that we learn, you understand, in physics, comes right back over to some other level of physics, right? So you never know that centripetal force would be in this, but it's actually in it, and centripetal force was in unit 1. So I mean, it's here and there, So we have to understand concept right across the board to be able to can master this thing. So having said all of that, guys, we can now come to the consensus that the force, the force that is being experienced on the charge is equal to the centripetal force. So that is why you're seeing this right here, to say that V times Q, which is the charge of the particle, times the velocity, is equal to mv squared upon r. Comprehend?
Yes, sir.
Oh, wonderful. All right. That's the main thing that we want to highlight here from this part, right? Now, we could have rearranged the equation to find r, which r would have been the radius of the circular path that the thing is moving around in, right? So there are just several things that we could have essentially found out here. All right. Now, we are going to look at something else here, right? Let me see. All right, so this is just explaining this before. All right, good. Now, there will be a point where, we can tie in electric fields and magnetic fields together, right? There's a point where we can tie them in together. Firstly, we're going to look at what happens when a charge is fired in between two charge plates. I don't know if you remember the whole thing about electric fields and all of that, but whenever you have two parallel plates, right? One, let me see. Let me make this one positively charged. This one is positively charged. This one is negatively charged, right? And if we know anything about capacitors work just the same, all right? So here we are now. We're just observing what is happening. By the way, there is a voltage that is applied to the plate, right? There's a voltage that is applied to the plate, right? I'm just basically redrawing this diagram here. Now, one of the things that you have to remember as well, from the mere fact we have a parallel plate, right? There are going to be electric field lines that are moving from the positive to the negative plate. So there will be electric field lines moving from positive to the negative plate. That's always how the electric field lines are. Now, if I have a negative charge, which is an electron, we must remember that you know, a positive and a negative attracts, right? Negative and negative repels. Also, positive and positive also repels. So if I were to fire an electron inside of this electric field, what you would see is that the electrons, or the electron here, would essentially move towards the positive plate. The reason why it would want to move towards the positive plate is because it would be experiencing a force of attraction. That is one way of looking at it. We could have also looked at it to say that it is experiencing a force of repulsion from the negative plate. You understand me? Right? We could have looked at it.
Can you say that one more time, please?
Yes. So here we have an electron that is fired perpendicularly, and I think we must highlight this, that it is fired perpendicularly to the magnetic field, to the electric field rather. When that occurs, what we're essentially seeing, right, that this negative charge is going to experience, it can experience two types of force, but the main type of force that it's going to really experience is a repulsive force. It's a repulsive force. The reason why it's experiencing a repulsive force is because this plate is negatively charged. So if you have the electrons coming in right here, right, and it's at this point, what you would see is that there will be a force that is going to push it up so that it goes towards the positive plate, because as we said, negative and negative repel. But at the same time, we could look at it to say that there is a force of attraction between the positive plate and the negative electron, because they are opposite to each other. But how we can look at it, or the best way to look at it, is by virtue of the fact that the negative plate would essentially be pushing the electrons up into the air. So because it's moving up into the air, then that is where the force is acting. So the force is acting upward on the electron. Anything that you want me to clarify or nothing? There's another thing that we should recall, right, as it pertains to parallel plates. Whenever we have parallel plates, there will be a distance of separation in between here, right? And because there's a voltage applied, depending on the distance of separation and the voltage that is applied, we can determine what will be the electric field, or the strength of the electric field. So to measure the electric field that is within this these plates right here, E, which stands for electric field, is equal to V upon D, right? So if I want to find the strength of the electric field, then I would simply need to know the voltage that is applied across the plate and the distance of separation between the plates to find out the strength of the electric field. Now, this is something that you can also see from this equation. If I were to increase the distance of the plate, my electric field would decrease because they are inversely proportional. By increasing the voltage across the plate, I increase the electric field. So that's one thing there that we ought to be able to pick up on. Now, we talked a while ago about the force. That the electron would have been experiencing as a result of the negative plate repelling the electron. Now, we can actually calculate and find that force. Now, if anybody remembers anything about electric field is the force experienced per unit charge. So electric field is the force experienced per unit charge. Having said all of that, I can transpose to find my force that will be exerted on the electron. So my force on the electron, right, would essentially be equal to the electric field multiplied by the charge of the electron. With all of that being said, I can simplify this equation to say that the force, right, that the electron is experiencing is equal to V times Q divided by D. All right? ¿Comprendes? ¿Sí?
Yes, sir.
All right.
Yes, sir.
Now, just for argument's sake, what if this was a positive charge? What do you think you would see happening here?
What, sir?
If my charge is now positive, if it's now a positive charge, what would be the change that would have been needed to be made right here? So the question is, what if the charge is no longer an electron, but it is now a positive charge, right? How would we expect it?
It would have been pushed downward instead.
It would essentially be pushed downward. So coming in, it would push down like this. It would push down like this. So in a sense now, there will be a force pushing down on the electron, right? Causing it to move towards the negative plate. This plate is negative. And as we know, positive attracts to negative, right? So that is essentially what is happening there. Now, I want you to see something here, because we're going to go into some more other stuff, and this will also involve unit 1 stuff, because what we're essentially seeing is that this thing is actually a projectile motion. It's actually a projectile motion taking place right here, right? So that now is going to take us into another realm of understanding certain things, right, about how the electrons work. But before we can go to that standpoint, we now have to look, look at the magnetic field, right? So this is for the magnetic field scenario, right? This is for the magnetic field. So let me see here. Let me see here. Okay. Yeah. So I mean, the main thing that we should remember, as we said, is that the force that this wire, that not this wire, but this electron here would essentially, because this electron is negative, right? You would expect that the force is acting in this direction. It's acting, once it enters the magnetic field, it's acting down like this, right? That's how it is working, right? So we understand this part because we would have looked at it previously to say that whenever we have an electron coming into a magnetic field, right, then you expect that this is how it would look. You see what I'm saying? This is how it would look, because we're treating the electron as going in the opposite direction as a positive charge. And with that being said, we would have seen that the force will be pushed downwards, you know, towards and going in a circular path. Now, there is a point, you see, where there is a whole thing where we can use both a magnetic field and electric field together. When we do that, right, we are essentially allowing the electrons to pass through the plates without being deviated, right? But it doesn't happen like that, because what you would have to do, you would have to make some adjustments so that your magnetic field, the force caused by the magnetic field, is equal to the force caused by the electric field. Once those two forces are equal, right, then what you would essentially see is that the electrons would pass through the plates and the magnetic field without being deviated, which means that it would not go towards any of the plates. So some amount of adjustment would need. So it says that the force acting on the charge, right, whenever we're dealing with the magnetic field, is given as force is equal to the magnetic field times the charge times the velocity. And that force is acting downwards. So that's a downward force, as you can see right here, that is acting downwards. It says in order for the charged particles to pass through the field undeviated, the electric force and the magnetic force must be equal. Must be equal. There are several ways we could have done this. One way we could have used is by changing the electric field, right? Because how you change the electric field is by changing the voltage, right? So if you change the voltage, then you can ultimately affect the electric field. So up to a point now, it will reach to a point where that particular voltage will cause the upward force to be equal to the downward force, right? And the downward force is the force caused by the magnetic field, right? And the upward force is the force caused by the negative plate repelling against the electron. So once we reach to a point of equilibrium, in a sense, or balancing, then what you would see is that the electrons would be passing through the plates undeviated, right? And that is when we're saying that the force caused by the electric field is equal to the force caused by the magnetic field, where we know the force of the magnetic field as B times Q times V, and we know that the force caused by the electric field as the E times Q, right? Now, what you're going to see here, let's just, let me see something here. At the end of the day, I believe these Q's are going to cancel out. These Q's are going to cancel out. So I think we're really left with, but I don't think you'll be doing that. But let's just leave the equation as that, right? So don't cancel out anything. Let's just leave the equation as that. So you just want to know that for now, right? Until the time comes when you really need to use that information. Okay. All right. This whole concept here, I don't like to talk about it. Like, I mean, it's a hard thing to understand. What we call the Van Allen radiation belt. This is just something that happens within the Earth, um, out of in space. In a sense, it occurs out in space. What we see happening, as you can imagine, that the Earth the Earth is a giant magnet. I don't know if you had known that, but the Earth is a giant magnet, and I know I'm not going to be able to can fully explain it, right? Another aspect of electric, well, magnetism, right? And I believe this is probably the last aspect of it, hopefully. Not completely, but is what we call a Hall's effect, right? Hall's effect. The thing about this guy, you see, this guy by the name of Hall was able to observe something spectacular, right, about electrons as how they move, right, in when when the electrons are actually passing through a conductor, right. Let me see here. Just give me a second. Yeah. So.
Okay, sir. I was just curious about this, like the Zoom. Like which one do you have? Because this never happens to me where it like runs out of time. I've been for like hours.
Oh, yeah, because I don't have money to waste, I guess, right? So that's the reason why it runs out.
I didn't purchase it either. So
But
that's why I'm curious.
yeah, I don't know. As I said, I don't know. I have it for a good while now. It's conditional. It's conditional because I've seen where it works like for long hours, one or two times. But the thing is, as I said, it depends on who, because some person can have a paid account. I don't know how to explain it, but yeah, um, I don't have a paid account though. But as it pertains to Hall's effect, this is something that we have to talk about. And it says how Hall's effect is the production of voltage across a conductor when current flows through the conductor at a right angle to the magnetic field. It says that a small current through the probe across the ends when the magnetic field is applied, electrons are pushed sideways by the magnetic field, hence accumulate along one side of the probe. Hall's effect and lack of electrons on one side resulting in an electric field between both sides. It says that the charge is detected by a small voltage across a probe called, we call this voltage the Hall's voltage. It says the greater the magnetic flux, the greater the Hall's voltage. We're going to just look at it from a diagram standpoint, right? So what we're literally seeing here is that whenever current, you see, is flowing through a wire, and we allow a magnetic field to pass through the wire perpendicularly, what we're seeing occurring here is that the magnetic field would cause the electrons to no longer move in a straight path. So at first, this was how the electrons would have been moving, right, going right across. Let me just, it can work like that, right? So this is how the electrons are moving, right? Current coming in, the electrons are moving right throughout here like this. But what you're seeing now is that when the magnetic field is applied to the material, the electrons are then pushed aside. So the electrons are pushed aside because, as you can imagine, the magnetic field is going to cause a magnetic force acting on the electron. So it's now allowing the electrons to be pushed towards one side of the conductor. Now, what we're going to see here is that if we were to take a voltmeter, a very sensitive voltmeter, right, and measure the what would I call it now? The voltage across this side and voltage across this side. you would realize that there would be a small voltage on the voltmeter. Let me just fix something here so you can see it a little bit better, right? But what we're saying, how the effect works is that charges flowing into the conductor, right, are going to be, essentially pushed to one side of the conductor. So in a sense, we have a lot of negative charge being accumulated on this side. And of course, if all of my electrons are pushed against this side, then it means that all of this side is going to have positive charge. So remember now, if you have positive charge on one side and negative charge on one side, you're essentially creating an electric field. So this is how the voltage is, set up across the entire conductor. And by just measuring both ends right here, you could essentially measure a small voltage called the Hall voltage. And I want to know what direction my charges are going to move. But based on this arrow, it shows me that this is the direction of the current, but it is not any type of current. It's the direction of the conventional current, which means that is basically the flow of positive charge. So if I were to actually use the Fleming's left-hand rule to find out where the electrons will be pushed towards, I would have to consider that the electrons are going that way. They are going up like this and not going down, right? So for that reason, if we go ahead and identify our magnetic field, let me see here, magnetic field going up. Let's see here. Magnetic field going up. All right, I'm not seeing it. If we do it the other way, would it work? What does conventional? Conventional current means current flowing in from positive to negative. I guess we have to use a conventional current here and not the flow of electrons. So it's a conventional current that we're using. So scratch the part about electrons flow a while ago. Scratch that part a while ago. It's actually the flow of the conventional current. That is what we have to use, because if we use the other one, it's not going to give us the accurate thing, right? So that part that I just said a while ago, while that is correct, right? But for this case, we're not going to use that to consider where the electrons are going to move. So let's now consider that the current is going like this. So if the current is going like this, right, and that your magnetic field is going up like this, by using the Fleming's left-hand rule, we could essentially see, right, we could see that my first finger is pointing up into the air, my second finger is pointing towards me, and then I'm going to see that the force is acting in that direction. So what that tells us is that the negative charge will be accumulated on this side or on this plate, as you're seeing from this diagram. Okay?
Yes, sir.
Now, as I would have pointed out to you guys already, is that if all of my negatives are going on this side, if all of my negative charge are going on that side, then it means, so this is what is happening. So the negatives are coming over here, right? If the negatives are moving on that side because of the magnetic force, then it means that this side is going to become positively charged. Hence why you're seeing these positives on this side. So this side is positively charged, and this side is negatively charged. Whenever you have positives and negative charge being set up, you're essentially going to have an electric field being generated, right? So how your electric field is moving, it's moving from positive to negative, positive to negative, positive to negative. But we don't stop there. what you're going to see occurring, guys, is that as the current continues to flow, more and more charges are going to be accumulated on this side. And when that occurs, it's going to change the electric field. It's going to change the electric field up to a point where the electric force, right, on the electron is going to be equal to the force that the magnetic field actually has. Because what you're going to see, let me show you. So as more and more electrons accumulate on this side, remember now that electrons repel each other. So if more electrons are coming on this side, then these electrons are going to be repelled, right? Now, whenever that occurs, that repulsive force, which is the force caused by the electric field, when that force is equal to there will be a point where that force is equal to the magnetic force, right? And then when that occurs, it means that the electrons will now pass through the metal undeviated. So once the electric force is equal to the magnetic force, the electrons here are going to pass through undeviated. Similar to what we looked at previously about the mutual perpendicular relationship between an electric field and a magnetic field. But just let me know if you guys see what we're saying here, and if you guys understand, Are you guys there?
Yes, sir.
So this information here, you will get to read it to just put things together in more perspective. Because at the end of the day, what we're actually trying to find is what Hall's voltage is. What's the Hall's voltage, right? That's what we're actually trying to find. All right. So we're going to prove something else before we go. But this is the part that says that the process continues until the magnetic force is equal to the electric force, and subsequently electrons pass through undeviated. All right. So we're going to just derive an equation, right, for our Hall's voltage. So clearly, we're seeing here that whenever the force caused by the magnetic field is equal to the force caused by the electric field, we know the force caused by the magnetic field is equal to B times Q times V, which is equal to the force caused by the electric field, which is equal to the electric field times Q, right? Now, recall that for the electric field, that electric field will be dependent on the Hall's voltage, right? So we're going to call this Hall's voltage divided by the distance between the plates. And we can go back to the diagram around here to see what we're talking about, right? So the distance between the plates, the distance right here between the plates, right? So we can replace this to say that E is equal to this voltage, the Hall's voltage, divided by D. Then you can see now that, let me just, before I do that, let me just erase this because there are more things coming out on the screen there. Right? So yeah, as I was saying just now, that the electric field is equal to the Hall's voltage divided by D. And if we go ahead and substitute, at first I had that B times Q times V is equal to E times Q. If I substitute for E, if I take this E, which is the electric field, and substitute it in this equation, I now get that B times Q times V is equal to H, Hall's voltage, right, divided by D times Q. Q and Q cancels out. So at the end of the day, our Hall's voltage is going to equal to B times the velocity, right, times the yes, you have to leave now. All right, no problem then. So I'm going to just finish the recording, and you can see the last part of it. All right. So we don't want to be on this part until we want to move on from something else. All right. But yeah. So at the end of the day, this is what we're now having to say that B times V times D is now equal to my Hall's voltage. So if you wanted to find your Hall's voltage, right, you can just remember this equation, or you can derive it. So that's the reason why we go through the derivation, so that you can remember equations, because it's not good to just swat it and all of that. So B times V, where V is the velocity of the electrons times the distance between the conductor, is equal to the Hall's voltage. Where it says that the velocity is not just any type of velocity, but it's what we call the drift velocity, right? What we call the drift velocity. And our drift velocity, as we can imagine from earlier days, that drift velocity is equal to the current divided by N times Q times A, where A speaks to the area, where Q speaks to the charge of the electron, right? And N speaks to what we call the charge density, or we can say the charge, the number of charge per unit volume, or per unit meter cube, right? In a sense, what we call the charge density. And I obviously is the current, right? This is taking us into another realm of deriving something here, a more different equation. Let me just see what's next. So this is kind of like the final equation, so to speak. But if you remember this one, you are on your way to winning the gold medal, right? But you should also remember though that the velocity of the electrons is what we call the drift velocity, and that is essentially equal to I divided by N times Q times A. I know it's a lot. I know it's a lot of information, but we are at the end of this part though, right? So the other information you can just read up on that to just see what a Hall's probe is. A Hall's probe is just the device that is used to measure the Hall's voltage, right? Or as a matter of fact, we can use it to measure the magnetic flux density, right? So that is just where we're going to stop it right here for this particular lesson.